on, again, ETGs and this time metallicity gradients.
Can you hear me? Right. Yes, thank you. So I'm going to tell you about the stellar metallicity gradients of manga early type galaxies. This is a work we've been doing here at UCSC with Kevin Bundy, Cal Westphal, and Francesco Belfiore. This work is motivated by the observation that early type galaxies at redshift 0 are a factor of 4 larger than those at redshift 2. So this is nicely captured by the work by van der Wel, 2014, for example, where we see in this figure in the x-axis redshift, in the y-axis effective radii in units of kiloparsecs, and this is for galaxies with a mass of 5 times 10 to the 10 solar masses. And the red points show early type galaxies. So we can see that from redshift 2, where the effective radius was of about 1 kiloparsec, this evolution is steep down to redshift 0, where the size is on average 4 kiloparsecs. So a lot of effort has been put trying to explain this size evolution, and mainly 2 explanations have been proposed. So the first one is in the form of progenitor bias. So this explains that as the universe grows older, new early type galaxies are being formed, and galaxies that are quenched at later times tend to be on average larger. So there's no intrinsic size evolution, but what happens is that these new galaxies that are joining the red sequence are larger, they drive the average effective radius up. The other explanation is growth via mergers. So as galaxies merge new systems, accrete lower mass systems onto their outskirts, they do not grow in mass very much, but they do in size. So a lot of effort has been put to try to tell which one of the 2 mechanisms is more responsible for the growth. And for example, the work by Genel 2018 on the illustrious hydrosimulation found that progenitor bias dominates in the low mass end. So here we have mass in the x-axis, and here we have size growth post-quenching. So we're looking at the red line here. The post-quenching size growth is important only at masses greater than 10 to the 10.5. So the conclusion is that progenitor bias dominates in the low to intermediate mass end, whereas mergers dominate in the high mass end. So then we can ask ourselves the question, if we focus on the minor merger mechanism, at what distances from the center of galaxies can we find these accreted stars? So this work, also on the illustrious simulation by Vicente Rodriguez Gomez, traces the stellar mass density profiles of in situ and ex situ stars. And the conclusion is that near the center of galaxies, in situ stars dominate, whereas in the outskirts, ex situ stars dominate. And the transition between the 2 tends to happen closer in, the higher the mass of your system. So at 10 to the 12 solar masses for stellar mass, the transition happens closer in, at radii smaller than 1 effective radius. So the implication is that radial stellar metallicity profiles of early type galaxies should somehow capture this transition from in situ to ex situ. And another work on the illustrious simulation by Cook 2016 has studied what they define as stellar metallicity gradients. So if you have a radial profile for the stellar metallicity and you fit a linear form to this profile, you can derive a gradient, which will have a negative value if the outer parts are more metal poor, or it will have a positive value if the radial profile is increasing with radius. So in this figure I'm showing here, we have in the x-axis velocity dispersion, central velocity dispersion, and the y-axis metallicity gradient. And they find that they tend to be negative, so the outer parts of early type galaxies tend to be more metal poor. But as you go towards higher and higher central velocity dispersions, these gradients get flatter. So the result is that simulations predict mergers to flatten the metallicity gradients of early type galaxies. So at this point, we know what these signatures should look like, signatures of minor mergers. They should look like gradient flattening. And we know where they should show up. They should show up in the high mass end. Then the question is, can we find the observational evidence to back this up? And the good news is that we have the data. So surveys like MANGA that provide spatially resolved spectroscopy and the large sample sizes to study these trends are becoming available in the past few years. So I'm going to summarize what the results have been so far based on the MANGA survey on this matter. So I'm showing here 3 different works on the same, based on the same survey, the MANGA survey. These 3 figures here show in the x-axis a proxy for the total stellar mass, and in the y-axis we have the metallicity gradients. They all tend to agree in the fact that they tend to be negative, but their conclusion on how the gradients depend on the total stellar mass of the system are not in agreement. So Sheng, 2017, conclude that there's no strong correlation between the gradients and the stellar mass. Goddard, on the other hand, conclude that, if anything, as you go towards higher masses, the gradients become steeper, which is the opposite of what minor mergers would suggest. And Lee, on the other hand, keep in mind that the axis here is inverted, find that the gradients get flatter as you go towards higher masses. So the takeaway point here is that there's no clear evidence yet supporting the minor merger scenario on the stellar metallicity gradients. So for this work, we proposed, so why don't we have another look at the MANGA data? We use the same Firefly code that was used by the Goddard paper, full spectral fitting metallicities, and we find, so we have in the x-axis mass again, the y-axis we have metallicity gradients, and then again, they tend to be negative, but there's no strong evidence suggesting that the higher mass end has flatter metallicity gradients. So no obvious evidence of merger signatures. So at this point, I'm going to propose, why don't we forget about fitting a linear gradient to a linear form to the stellar metallicity profile and derive a gradient, and why don't we look at the actual average or median stellar metallicity profiles as a function of mass. This is what I'm going to show here. So this is radius in effective radius units, and the x-axis, in the y-axis we have stellar mass. And notice how going from 10 to the 9.5 solar masses up to 10 to the 11.5, there's a clear evolution in how flat the gradient is in the region from 1 to 2.5 effective radii. So I'm going to summarize the results from this figure using 4 bullet points. The first one is that the average profiles are not linear. So you can imagine that if you fit a linear profile to this, a linear form to these profiles, you're going to you will not be able to capture all the signatures that you're after. And that's going to wash out any signatures given that they are already very subtle. So we conclude that the steepness of the profile anti-correlates with stellar mass, which is consistent with the minor merger picture. So now I propose we go back to the title slide where we said the stellar metallicity gradients of MANGA early type galaxies. I hopefully have convinced you that we should be talking about the profiles and not the gradients. There's a lot of information in the profiles that are hard to capture just computing a metallicity gradient. Okay, so we found that these signatures are consistent with accretion, but where do we go next? So we want to show, we want to find whether these trends have any dependence on environment, right? Because higher density environments should in principle have the required conditions for minor mergers to happen. So the figures I'm going to show are preliminary work, but just to show you what we're doing right now, we're exploring on how the gradients depend on whether galaxies are centrals or satellites at fixed stellar mass. And also studying how these gradients depend on large-scale structure. And we're finding interesting trends, but as I was saying, this is preliminary work, so I'll stop here and take questions. Thank you.
Thank you. Any questions before the coffee? Yeah. Can you speak loud?
Very, very cool. So for example, in this plot in the bottom left, those are the most massive ones, right? Yeah. So you can see like a break in the slope. So do you think that's an indication of like in situ dominated versus ex situ dominated regions? Or
so you're looking at centrals or satellites? Satellites are pink here.
Oh, those are satellites. Right.
Yeah. So
right.
like as you can see, the error bars for satellites here are very large.
Okay. Okay, and one last question. Have you looked at like signatures of disturbed morphologies, like the asymmetry of the galaxy or something? That could be like an independent indication of maybe recent merger activity. That could be something.
Yeah, so for now we're just looking at the stellar populations. But so for that, I guess that would be more like this DSS kind of work that you would do, because if you're interested in stellar populations, that's what manga excels at, I would say. So I mean, you could basically start selecting a sample from manga and then look at what happens in the images, which would be interesting.
I do have a quick question. So you claim that we should look at the profiles instead of the gradients.
Yep.
However, the idea of looking at the gradients and looking for a signature in the gradients came from simulations, because in the simulation you see a signal. So the fact that you see it in the simulations, you don't see it in the data, is telling you something, or it's just noise, or?
So that's a very good question, actually. Let me go back to this figure. So this flattening that you see here, this is for the stellar halo. So this is 2 to 4 RE, which is what comes in terms of radial coverage right after what manga is sampling. So in the outer galaxy between 1 and 2 RE, it's not so evident from simulations. So this may be also a consequence of the gradient, of using the gradient. So if the trends are really obvious in the stellar halo, but not so much in the outer galaxy, simulations can also be affected by the fact of simplifying the profile by using a gradient.
Yeah, David.
You can analyze this with the last figure showing the differences perhaps between centrals and satellites and the environment, but you didn't show that for the other data. I was wondering whether you looked at it already and did not see anything, or why did you not comment on that?
Oh, so you mean this work?
Yes, that's correct.
Okay. So it depends on which work. So the Zheng and Goddard, they look at different environments and they find no correlation with environment. So I don't think they go into centrals or satellites. They do the same like large-scale structure comparison in Zheng. In Goddard, they do the analysis based on some other environmental tracers, but not central satellites. So I don't think any of these works have actually looked at central versus satellites, but I would need to confirm to be sure.
You could do that for your sample without the profile.
You mean using the gradients?
Yes.
Yeah. But the the point we're trying to make is that if you look at here, so if you were to fit a gradient to centrals and satellites here, would you see a difference? Probably not, right? Or here, probably not, right? But looking at the profile is what's telling you that there's a difference between the two.
There's an offset.
Yeah, there's an offset.
That would be interesting to see. Global.
But like
offset is already an indication that you might see it actually global numbers, not just between the. You might see, because of these offsets, there's actually should be a signal that you would see globally without the profile analysis.
you mean using the total metallicity?
Correct.
Oh yeah. So I don't know if you're familiar with the paper by Pasquale, based on Sloan galaxies, but they find that the metallicity of satellites and centrals, the total metallicity, I think it's based on Atlas 3D data, seems to be different between centrals. So we're extending this to the whole profile.
I'm not disagreeing.
No. I'm just, yeah.
Okay. Let's thank Grecco and all the speakers of the morning.